Okay, so now we're to the point where what happens if it's inputted, our data is inputted in the computer, and then how do we read this output? So we're looking at computer output and trying to look at what it means, because there are three main programs that statisticians use. We have JMP, JMP, we have Minitab, which is really, really expensive, thousands and thousands of dollars. I was lucky enough to get a teacher edition for $100. And then there's Fathom, which can rent out to students for about $20 a year, or you can buy it on your own for about $80. And so when we enter in this information into the computers, we get different types of outputs. And so knowing how to read that and understand what's happening is really important. So this is Minitab. We tend to like Minitab because it gives us some of the best outputs around. The best graphs, everything. It does anything and everything, and it's pretty amazing once you get to know it. Plus, it works really well with Excel. So a lot of people like that. So what happens here is we have this output, and it tells us right away what our explanatory variable is. So our explanatory variable here is body weight. We use body weight to help predict what they tell us up here, pack weight. So our example is body weight in pack weight, and body weight is our x variable. And then across from our x tells you the slope of the line. So this is my slope, also known as our B1. And right above it is our constant. So it's kind of like our beginning value. This is our y-intercept. Now we have other variables over here like the standard error, the t-value, the p-value. That's stuff that we're going to use second semester, all really important to running statistical tests. But the stuff that we've talked about so far is our r squared and our s value. So when we're looking at the questions here, they ask, what is the equation for the regression line? So our equation would be y hat equals, and then we put in our slope, 0.09080. Oops. And that's times x, and then plus 16.265. Not written on our standard statistical form. Our correct statistical form would look like y hat equals 16.265 plus 0.09080x. And then typically you'd say y hat is predicted pack weight because you're always labeling these in context. And then our x is our, I don't know why I put x bar. X is our body weight. So this is what really should be up there. Okay, what's our typical prediction error? So we have to remember what's our prediction error? And our prediction error is S. So our typical prediction error is 2.26954. And this is a prediction error in our y value. So if our y value is pack weight, this is 2.26954 pounds of pack weight. What is the coefficient of determination? Well, that's our r squared, which is 63.2%. It doesn't ask us to interpret that, but if we were, that would be 63.2% of the variation of our pack weight can be explained by the linear regression line. Okay, correlation. They don't tell us r. But luckily we know r squared. So r is going to be the square root of 63.2% written as a proportion. So we're going to go ahead and calculate that. And we get 0.79 .4984. We get the idea about a correlation of 0.79. So almost strong, and that's it. So let's look at our next one. We have the used Hondas Minitab output. Same idea. Our explanatory variable is miles. And if you remember correctly, our response variable was cost. And then here's our slope, here's our y-intercept. So when I write my equation, y hat equals 18,773. Oh, when I get too close, it's hard to read. So it looks like 0.3 minus 86.18x. Typical prediction error is our S. 971.647. And this is cost, so this is dollars. Coefficient of determination, that's our R squared. That's 76.4. Almost grabbed the wrong R squared. And then for our correlation, we're going to go ahead and square root the R squared. 0.764. I've got to change it into a proportion first. Which gives me a correlation of 0.874. And that's it. Okay, let's keep on going because there's more here. Okay, now we have a jump output. So it's a little different looking. We have got our age and reading scores. And again, kind of like our Minitab, our age was our X value. And then they went ahead and they put intercept instead of constant, but that's okay. Here's our slope. Here's our y-intercept. So when I write my equation, y hat equals, oh, it's hard to read from so close, 109.873 84, and then minus, because my slope is negative, 1.126989 x. What's our typical prediction error? This is our S value. Which is our, and our S value is that root mean square error. So our S value, wow, that's quite a big amount of error. 11.02291. And this is measured in age and reading scores. So reading score, maybe not so much when you take into consideration that we're starting at 109. The coefficient of determination, that's our R squared. So we use R squared, not R squared adjusted, 0.409971. This is not turned into a percentage, so we would translate it into a percentage for our interpretation purposes. But what's nice about it being written as a proportion is you don't accidentally make a mistake when you're doing your square root. To find your R. So this gives us a correlation of 0.640289, so on and so forth. Which gives us just enough. Okay, let's look at correlation and regression wisdom. So remember that correlation and regression are very powerful tools, but they do have their limitations. So please remember that when you are doing regression lines, so when you're doing regression lines, Explanatory variables and response variables are really important. Making sure you have the right thing in the right spot, because we do get different equations. So when we're looking at this equation versus this equation, they're very different because these have been switched around. Now, what does not change is your correlation and your R squared. So if you look at that R squared, that is the same. It doesn't matter if you flip-flop them. Correlation doesn't change with the flip-flopping, but it will definitely affect your regression equation. So please make sure beforehand you are determining what you plan to be your explanatory and your response, and you keep it that way. Okay. Correlation and regression lines describe only linear relationships. Please be careful about calculating without graphing the data. All of the data sets below have the same regression equation. So we've got data set A, data set B, C, and D. All the same regression equation, but look how different the data is. So in our first one, this line maps really well with our data points. But on this one, this doesn't map as well because as you see, there's definitely a curve. So we should not have used linear regression on that because of that curve. On data C, this line isn't going to be as accurate because we have that outlier up there. And that outlier is affecting that line. And then this one, data set D, we've got all these points over here and one point out there, that influential point that is really affecting that. And so always graph it first and see what's happening. See if it's really appropriate to use this linear regression, because otherwise you're going to spend all this time for no reason. And remember that these are not resistant, which means if we have these influential points or outliers, it's really going to affect what's happening. And the last thing we're going to talk about is association versus causation, and I've hinted to it all chapter long. Please remember that if it has a high correlation, there's a strong association. It doesn't mean that there's causation. And the only thing that we have that can really show us that there's causation is doing a really well-run experiment. An experiment where we randomly assign treatments. There's a control group to help compare for those and take care of the lurking variables involved. So, just to kind of point this out, there's a serious study once found that people with 2 cars live longer than people who only own 1 car. Owning 3 cars is even better, and so on. There's a substantial positive correlation between the number of cars, X, and the length of life, Y. And so then we sit here and we think about, well, yeah, of course there's an association, but what other factors are better explanatory factors there that might explain that? And so that might be something as simple as the income. If you have a lot more income, you're probably more likely to go to the doctor, eat healthier, all that sort of stuff, and that might better predict your length of life. And so all these other things that may pony up, you've got to think about what's really happening there. So there is this website. Let's see if we can get this to pop up. Tyler Vegan. And he's got this great website, and I'll go ahead and put the link on my site, so if you want to come check it out at any point in time. He's got this site called Spurious Correlations. And so what it does is it takes a look at these different correlations that exist, and you think, oh, it's got to have this high correlation, so it's got to be important, and all that, and really a high correlation does not mean anything. So here's our first graph, and it compares spending on science and space and technology with suicides by hanging, strangulation, and suffocation. The correlation is really high, 99.79%, a 0.9978 correlation. Really, really high correlation, but I don't think us spending a lot of money on science and space and technology really affects what's happening with hanging suicides. So just because there's association doesn't mean there's a causation. Number of people who drowned by falling into a pool correlates with films that Nicolas Cage appeared in. A correlation of 0.666604004. Wow, that's pretty crazy. This one's one of my favorites. Cheese consumption. Per capita cheese consumption and number of people who died by becoming tangled in their bed sheets. Cheese consumed. That's crazy. A 0.947 correlation between cheese consumption and people who became tangled in their bed sheets. All sorts of craziness there. Divorce rate in Maine, per capita consumption of margarine. Age of Miss America, murders by steam vapors and hot objects. Revenue by arcade, computer science doctorates awarded in the US. So all sorts of things that end up with some high correlations that just really emphasize the idea that just because it has a high correlation doesn't mean that there's any sort of causation. There's just some sort of relationship possibly there, or it's a coincidence. So that's it for chapter 3.